Okay. Hi, everyone. Good afternoon. It's a pleasure to be here to start the second part of our workshop. And we will begin with Professor Alex Freitas from the University of Kent. And the title of his talk is Machine Learning for Aging Research. Alex?
Okay, let me share my screen.
The title of his talk is Machine Learning for Aging Research. Alex?
Okay, can you see my screen?
Yes.
Okay, good. Okay, so as Plastino said, the title is Machine Learning for Aging Research. Let me just try to maximize it here. Okay, so basically this is a kind of interdisciplinary talk combining both machine learning and the analysis of data about the biology of aging. So as an introduction to aging, most people think about the aging as something which is inevitable, which is directly associated with the passage of time. And of course, aging is related to the passage of time, but there is also an important difference because in principle, one particular species, for instance, could experience passage of time without aging if there is no loss of a physiological function. So what really characterizes aging from a biological perspective is not only the passage of time, but the progressive functional decline or a gradual deterioration of physiological function. In the specific case of humans, for instance, that means the risk of death, unfortunately, doubles every 7 or 8 years. Those figures vary a lot across species, and within a same species, there is also a lot of variation among individuals. So if you consider two people of the same chronological age, very often they're going to have very different biological ages, although that's difficult to estimate. And actually, one current hot topic of research in age is precisely how exactly we can measure biological age. But it's normally accepted that different people age at different speeds. So the motivation to do research on aging itself, not just age-related diseases, is summarized, I believe, in this slide. If you look at this picture here, you can see that I put here several examples of age-related disease at the top, things like cancer, Alzheimer's, diabetes, cardiovascular disease, and so on. I could put a number of others there, okay? But they all have in common, they're quite different from each other, but they all have in common the fact that the ultimate cause of all those diseases is basically the process of aging, at least according to the following perspective. Many people die of each of those diseases, but if you check, of course, the death certificate, it's not going to be written there, died because of old age. The immediate cause of death is going to be eventually one of those diseases. But the fact is, in the majority of the cases, they would not die, they would not even have that disease in the first place if they were, let's say, 20 or 30 years younger. So clearly, aging is not the immediate, but the ultimate cause for a number of age-related disease. And that realization is important because that means that if you are really serious about improving human health in general, we have to do something about the process of age as a whole, because the traditional approach of coping with one disease at a time is no longer very effective as it used to be 20 or 30 years ago. Because now people are living longer and longer. And as they live longer, they started to suffer from not just one, but multiple of those age-related diseases at the same time. So even if you could magically cure one of those diseases, which is already extremely difficult because each of them is a very complicated disease, but even if you could completely cure one of them, the patient would still be suffering probably from other disease. So really, in order to improve the health of people in general, we need to do something about the process of aging. The idea is to slow down the process of aging, ideally by discovering some intervention, for instance, maybe some medical drug or another type of intervention, which slows down aging without too much side effect, obviously, so that we can improve the health of the individual as well. So the idea is to improve the so-called healthy lifespan, the period of life where the person is experiencing good health before they started to suffer age-related disease. So if we can postpone the beginning of those diseases, that's a huge benefit for the population. And that's become, as I said, even more urgent, more and more importantly, as the population grows older. So in terms of the worldwide population, roughly speaking, about 5 or 6 years ago, only about 12.3% of the population were aged 60 years or over. Now, in 2030, just about 9 years from now, that's going to increase to 16.4%. And by 2050, it's estimated that about 21% of the world population will be over 60 years old. So that will put a huge pressure, socioeconomic pressure, financial pressure, medical treatment pressure on the population, because it's very difficult for national health systems to cope with this huge demand if all those age-related diseases showing up at the same time. So we have to do something about the aging process as a whole. But the next question is, what can we do in terms of using machine learning? Because aging is fundamentally a biological, biomedical problem. So the question is, can we really use machine learning to do research in that area? And it turns out that yes, we can, and there is at least one motivation to do that. The motivation is that it is very, very hard to collect data from wet lab experiments with humans, especially because human age is a very slow process which happens over decades. It's very difficult. Very few organizations have the resources to keep following a population of individuals for decades, taking blood samples every year, every 2 years, to observe really what happens over 20, 30, 40 years. So most of the research on aging by far is done with the so-called model organisms. Organisms like mice, flies, where it's a lot easier to get the data because they have much shorter lifespan, okay? And there is a growing amount of data about those age-related databases, both from humans in some cases, in the few cases where we have human data, and in the case of animal data, there is more and more now information about those aging experiments found on databases available on the web, including the longitudinal studies of the human age. So given that data intuitively, we can apply machine learning to extract some new age-related patterns, hopefully, from such a database. The caveat is that it's going to be, at the end of the day, just some computational experiment. It's never going to be as conclusive as doing a wet lab experiment. You are not going to convince a medical doctor, a biologist, just with the result of some machine learning experiment. But machine learning has the advantage of being a lot faster than doing a wet lab experiment. And hopefully, we can at least discover some aging-related patterns which can give a reasonable clue to a biologist or medical doctor about what types of genes they should investigate more, what type of medical conditions they should pay more attention in order to understand more about the process of aging from a more holistic perspective. So the idea is to discover something which can help guiding the decision about which biomedical experiment will be done later, which is a much more expensive, much more time-consuming experiment. So before I move on now, just to give you a brief overview of the type of machine learning task that we are going to discuss. I assume many people here in this presentation know about this thing already, but just to make sure that we are on the same page, the talk is about the classification task of machine learning. So the basic idea is that we have a set of variables. Technically speaking, we have two types of variables. We have the predictive features, and we have the class variable, which is a special variable. So we have to do a prediction of the value of the class variable based on the values of the predictive features. That's what the machine learning algorithm has to learn. It has to learn the relationships between the predictive features and the class variable. And we let the algorithm learn those relationships from a training set where the algorithm has access to the values of the class. And then we validate, we measure the accuracy of those predictions on a test set where the algorithm does not have access to the real class of the example. So basically, we are measuring here the generalization ability of the algorithm to predict the values of the class labels in the test set based on the training performance using the training set. Now, broadly speaking, there are two types of machine learning research that we do here at the University of Kent. Most of my research actually is about the first topic here, research using data sets of age-related genes and the proteins. So in this case, this is kind of a bioinformatics research because the data is mainly data about the genes or proteins involving the molecular biology of aging. And most of this data comes from model organisms due to the difficulty of collecting human data, as I mentioned before. So as an example of this line of research, Marcelo Meyer, a PhD student at UF and currently a visiting PhD student here at Kent, is going to give a talk after my talk. So it will be about this line of research. In the remainder of the talk, I'm going to discuss a second type of approach to use machine learning to study aging, which is applying machine learning to data sets of human longitudinal aging. So I'm going to focus on one particular case study where we try to predict if an individual will develop age-related diseases in longitudinal data sets. And the basic idea of this case study is that we propose some kind of a variation of a well-known machine learning algorithm, classifier, random forest, where we modify the algorithm to be more suitable for coping specifically with the longitudinal nature of the data, the temporal nature of the data. So by longitudinal data, what I mean is data containing variables which are repeatedly measured over time, which normally in the literature is called the waves. So wave here is just a time point. So you may be more familiar perhaps with time series. Time series is a very common type of data involving temporal information. Longitudinal data is related to some extent to time series, but it has some difference. Time series normally is about the numerical variables, whereas in the case of longitudinal data, we can have a mixture of numerical and categorical nominal variables. Also, time series usually has just one variable. You may have multiple variables, less common, but still possible. But even if you have many variables, normally you don't have a large number of variables. Whereas in the context of longitudinal data, normally you have a large number of variables. And in time series, normally the number of data points is very large. Whereas in longitudinal data is the opposite. You have many variables, but the number of time points is relatively small. So in that context, there are a few databases of longitudinal human aging which are available free of charge on the web. Anyone can access those databases. We are going to focus here on the first one in this slide, which is the English Longitudinal Study of Aging, which has about 12,000 participants. But just to mention briefly, there are others like the Irish one, other countries have equivalent databases. There is a much larger one for the European Union as a whole with more than 100,000 participants, the share one, and so on. If you're interested in this kind of databases, my PhD student who has done this kind of work, he also published a survey paper here summarizing the main characteristics of these databases and the opportunity for applying machine learning to them. Okay, so now in order to apply machine learning to this kind of database, the first step is to create a data set suitable for the classification task. Because if you get the raw data from the database, normally you cannot apply directly the machine learning algorithm. It's not very clear what the class variable is going to be, what are the predictive features. There is a lot of redundant variables. Many variables are duplicated. They measure things which don't make sense from a machine learning perspective. So you have to spend a lot of time preparing the data. But after you do that, you can put the data in a standard format for a classification algorithm. So in the case of this particular ELSA database, the data consists of people who are all of them at least 50 years old, and they are followed over a number of years. And every 2 years, there is an interview to collect more detailed data about each participant. So that's called a wave. And every 2 waves, which means every 4 years, the process goes a bit further. A nurse visits the person and they collect some biomedical data. So in this case study, we are interested mainly in this biomedical data, which hopefully has greater predictive power, because the data also has a large number of variables which are psychological variables, socioeconomic variables, whether or not the person is retired, even detailed information like, how often you watch TV every day, those kinds of things. We don't want to use that kind of information for predicting age-related disease. So we are focusing just on the biomedical variables. So after creating the data set, it has about 7,000 instance examples, about 140 biomedical predictive features spread across 4 waves. And there are 10 different data sets varying the target variable, the disease that we use as the class variable. We don't vary the predictive features across those 10 data sets. So there are 10 data sets varying the target class variable, but all of them with the same set of about 140 features. And the list of the diseases are things like that: arthritis, high blood pressure, cataracts, and so on. Okay, now if you wanted to apply machine learning to this type of data, you have some options. So the first option, which is not what you are doing, but just to show you what would be the baseline option, a kind of a naive option that you could very, very easily apply. The first option would be to aggregate all the data from those different time points, those different waves, put them all together in a single big table. In that case, the first feature here will be feature number 1 and so on until feature number n. Then the next feature would just add the next number here, the index of the feature. You would just keep adding sequentially the numbers. So if we have like 140 features in the first wave, the next feature would be simply feature number 141. So you could do that, but if you do that, you lose information about the time index because you wouldn't be able to recognize, the algorithm wouldn't be able to recognize that the feature in position 1 and the feature in position 141, they're basically the same concept of feature. For instance, cholesterol, maybe, the level of cholesterol. The difference that one is measuring the level of cholesterol in one wave, the other is measuring the level of cholesterol in another wave, in our case, 4 years later. So it is intuitively, it's important to capture this notion of time so that the algorithm has more information and hopefully the algorithm can make some intelligent decision about how to consider the time information into account when deciding which features are more important for classification. So that's the essence of the idea of the modification that we're going to propose. So what we do is something like that. We put the features together from different waves, but we preserve the time index of the features. So we have here now 2 subscripts here, one defining the number of the feature just sequentially by the type of feature, cholesterol 1, and so on. And then the second index here is the time index, the wave number. So now the algorithm has access to the time index and you can take that into account. So the basic idea of the modification of the algorithm in order to consider the time index is to modify the way that a random forest algorithm selects the most important feature in each node of the decision tree. So the basic idea of a random forest algorithm is to learn lots of different decision trees, and each node you have to select the most important feature for classification. And then normally that selection is performed by measuring only the predictive power of the features. You choose at each node the feature which seems to have the greatest predictive power to predict the class. In our case, we still take into account mainly the predictive power as the first criterion, but as a secondary criterion, a kind of tie-break criterion, we use the time index. So if 2 features have a very similar predictive power within a certain very small threshold, then as a tie-break criterion, we choose the most recent feature. So the idea is that, for instance, intuitively, it's better to predict a cardiovascular disease using the value of cholesterol now rather than the value of cholesterol 10 years ago, for instance. Clearly, the most recent value intuitively should be more important for this kind of prediction. So we can see that as one way of introducing some kind of background knowledge into the algorithm, because now the algorithm is taking into account this background knowledge, common sense knowledge, that the most recent features should have more importance for prediction. And we call that a lexicographic criterion because the name here comes from the analogy with the kind of lexicographic search that we do when you look up in a dictionary. First, you look at the first letter. When there is a tie in the first letter, you check the second letter of the word that you are trying to find and so on. So one step at a time, one verb at a time. So that's what you consider here, one criterion at a time. Okay, so I'll show you now 2 results quickly, just an overview. We have lots of experience with summarizing. We measured three different measures of performance on the test set, doing cross-validation, involving the percentage of the true negative rates, the percentage of negative examples which don't have the disease, which are correctly predicted as negative, the sensitivity or the true positive rates, and the geometric mean of those 2 measures. And I'm summarizing here at the bottom of the table the number of wins for each approach. So overall, as expected, the lexicographic approach achieves a higher predictive performance for all the three measures, although the difference is statistically significant in only one of the three measures. So it makes sense from a predictive performance perspective. But another perspective is, what about the insights, the patterns that we would like to extract from the data, to discuss that with biomedical scientists, to try to see if we are really discovering something interesting to understand more about the process of aging. Now, for that kind of analysis, random forest arguably is not the ideal algorithm because it's a black box classifier. It's a very powerful classification algorithm, but the model itself, the classification model, is a black box. So you need to do something to interpret the output of the random forest. So one way of doing that interpretation is to compute some measure of feature importance for each of the features in the data sets according to how important they are within the random forest model. Okay, so there are several ways of doing that. We are using the standard measure in the random forest algorithm that we implemented, which basically involves the compute the average class impurity decrease. So the greater the decrease in the class impurity after you select a feature, the more important that the feature is, and the higher the rank of that feature. So by doing that kind of analysis, we can then plot the results in this kind of table here, where we have here some of the most important variables, and I'm putting here just the information whether or not each of those predictive features is within the set of the 10 most important features according to that variable importance measure for each of the 10 data sets, predicting each of the 10 different diseases. So you can see that, yes, there is some kind of a correlation here. Some features are predictive of not just one particular disease, but several diseases, okay? HDL level, for instance, the so-called good cholesterol, okay? It helps to predict the occurrence of not just one, but several diseases. The same thing about the hemoglobin level, IGF-1, insulin growth factor, things like that, okay? Okay, so that was an overview of this particular study. I would like to acknowledge now my PhD student, Caio Ribeiro, who did all those experiments, implemented this variation of the random forest algorithm that I summarized here. And also my long-time collaborator, biologist at the University of Liverpool, Dr. João Pedro de Magalhães. And I'm now available to answer any questions about this. Thank you.
Okay, Alex, thank you very much for your talk. Excellent talk. I have two questions, but let me see if someone else. Yes, Deborah has one. Do you want to start, Deborah?
Yeah, it's a simple question. I think that I missed in your explanation. What do you mean by when you presented those performance metrics, lexicograph and not lexicograph result?
Yeah, so the lexicographic approach are the results for the version of the lexicographic random forest which I described. And the no lexicographic just means the standard random forest without using any lexicographic approach. Okay, it's just the baseline, it's just the standard algorithm without any modification.
Okay. And what kind of techniques are you using to explain the result, as you said that random forest?
Yeah, so once you build a random forest, you cannot interpret the random forest directly because there are too many trees, 1,000 trees, whatever, so that's not directly interpretable. But what you can do, you can take a look at the occurrence of the features within the random forest, and then you can compute a measure of how important each of the features is within the context of the random forest. Okay, so for instance, one particular feature might have been chosen very often to learn the decision trees within the forest. And in general, when the feature is chosen, that helps to decrease a lot the class impurity, which is the main measure that could be like the information gain, entropy, Gini index, several measures of class impurity. But okay, so but the point is, once you select a feature to put in a decision tree within your random forest model, you also know how much class impurity you are reducing. You want to minimize the class impurity. So the greater the reduction in the class impurity, the greater the importance of that feature within the random forest. So that information can be computed as a kind of side effect of learning the model. So you can report at the end not only the predicted performance, but also those measures of predicted performance, and that's one of them. Measures of feature importance. So that's one of them. There are others, but that's a relatively straightforward way of measuring the importance of a feature within the random forest model.
Okay, thank you, Alex. Thank you for your presentation. Very nice.
No problem.
Okay, thank you,
I have
Deborah.
a question.
Yes, do you want, Leticia? Okay.
Thank you, Alex, for the presentation. And my question is very fast. Is there any correlation between the features? I mean, blood pressure and cholesterol, and it is important how to deal with this?
Yes, we expected that there is a lot of correlation. That's very different from classical statistical analysis where you start more or less by assuming that the features are independent. So the large majority of machine learning research, including this particular algorithm, random forest algorithm, the algorithm is extremely non-linear, okay? It does not make any assumption at all about the independence of the features. So there might be strong correlations. The algorithm does not care. The point of the algorithm is precisely to detect those correlations which are non-linear, okay? So the algorithm copes with that in a more or less natural way. So that's part of the motivation to use this kind of machine learning algorithm as opposed to use classical statistics where you would need to make assumptions that the features are independent. We never make that assumption in machine learning. We just use a highly non-linear classifier like random forest.
Okay, thank you.
Okay.
Okay. Alex, if I understood correctly, you use each point of the time series as an attribute, don't you?
You have a series of waves, okay, which more or less equivalent to one point of time series. So for each of that wave, you have 140 features. So if you think about a feature like cholesterol, so there will be one value of cholesterol. I have just 4 waves, okay? So there will be one value of cholesterol for wave 1, another value of cholesterol for wave 2, another for wave 3, and another for wave 4. So I have in total 4 values of cholesterol, one for each wave.
Okay, so they are 4 attributes that represent this time series.
Yes,
And,
yes.
Yes. And have you thought about using the time series as a unit? Not each point of it, but for example, you could consider the form of it as a feature of this time series.
Yes, you could somehow summarize, you could aggregate, transform the flattening the time. Yeah, that's another approach, which I didn't show here. But you could, for instance, first you could compute some kind of arithmetic average. If the feature is numerical, you could compute the arithmetic average of the feature, like the cholesterol, on average over the 4 waves. But if you do that, you lose a very valuable information, including the most recent value of the cholesterol, presumably, which is particularly important, I would say. But you could do other transformations which still take that information into account. You could detect, for instance, monotonicity. So you could observe the values of cholesterol across the 4 waves, and then you could observe if the value has been steadily increasing or steadily decreasing over time. So, and you could have a kind of a feature there with 3 possible values maybe. 1 if it's monotonically increasing, -1 if it's monotonically decreasing, or 0 if it fluctuates. That's another possibility. But even if you did that, I would argue that it would still be good to keep the original features, particularly the most recent features, because if you completely replace the original features by those aggregated features, I think you'd be losing very valuable information. So the ideal scenario perhaps is to combine the two. You can keep all the original features, but on top of that, you can add the constructed features, aggregated features, and we have done experience with that as well, but I didn't put it here in the presentation in the interest of time. But my PhD student, Kyle, he has done experiments with lots of different aggregated types of features as well.
Nice, very nice. My second question is related to the identification of genes related to aging.
Yeah.
What's missing to make possible the study on human genomes? What do we need to do that? Because we have been studying with mice and other.
Yes, but in the case of mice, for instance, we can do the following experiment. you get a very young mice, so even before the mice is born, you can manipulate the embryo of the mice, whatever. You can do some very nasty experiment from the perspective of the mice. You can delete one gene in the mice, okay? So you delete one gene and you observe what happens with the mice as the mice grows. And what can happen there? Well, the most likely scenario if you're deleting one gene is that the mice is going to die a lot earlier. Or the mice may have a terrible life, suffer from terrible diseases, or if you're very lucky, once you delete a gene, the mice is going to live longer. But once you do this experiment anyway, now you have some nice results for machine learning, because you can find a correlation now between genes, and then you can describe the genes by a number of properties, and then the value of the class variable, which is whether or not that the gene is increasing or decreasing the lifespan of the organism. You cannot do that experiment with humans because it's extremely unethical. You're never going to get approval for doing that kind of experiment. Okay, so in the case of the humans, the best that you can do, you can try to observe the variation which already happens in the humans who are already alive today. So you can get a group of individuals, measure all their genome. You can sequence their genome. You can measure their level of gene expression, but that's not a controlled experiment, because you are not systematically deleting one gene and making one gene to be overexpressed. We are never going to be able to do that experiment with humans. So there will always be a huge gap between experiments with mice, with flies, where you can do pretty much what we want, given some regulations, of course, for animal ethics, that kind of stuff. But by comparison with humans, it's extremely more complicated, much more ethically challenging to do experiments with humans. Not to mention technical complications as well, because the human genome is much more complicated than the genome of flies, mice, etc. But the main issue, I think, is the ethical issue.
Yeah, very challenging. Very nice. Okay, there is another question from Petrúcio Ricardo. Professor Freitas, I believe that the hemoglobin level changed in the face of diabetes disease. Could you explain about this result?
I wouldn't be able to give you an explanation now. What I can tell you is that the definition of diabetes involves the level of one particular type of protein there, which is, I forgot the name now. So there is a correlation, but I wouldn't be able to explain that now. But if you really want to know that, you can send me an email later. I can try to talk to my collaborators to explain that to you, maybe.
Okay, Alex, thank you very much for your talk, for your answers. And we will now call Marcelo Maia from Institute of Computing, UF. And the title of his work is Random Forest for Uncertain Data about Aging-Related Genes. Marcelo, are you there?
Alex, could you please stop sharing your screen?
Okay, I'm trying to find out here. I'm trying to maximize the screen here. Hold on. Okay, now I got it. Okay.
Okay, I have done it for you. Thank you.
Okay, yeah, okay, yes, I got it now. Okay, thanks.
Thank you.
Hello, Faustino. Hello, everyone.
Okay, you're welcome, Marcelo. You can start when you're ready.
Let me share my presentation.
Just to introduce Marcelo, Marcelo is a PhD student that is working under my supervision and supervision also of Alex Freitas, and he will present his work. Okay.
Can you see my presentation?
Yes.
All right. Well, like Professor Plastino said, I'm a PhD student in UFF, and I'm currently working here at the University of Kent with Professor Lex. And in this project, we've been exploring some adaptations of random forests for coping with uncertain data in the classification of aging-related genes. And in this problem, we aim to build a model capable of predicting the class of an aging-related gene, where the possible classes are anti-longevity, and longevity. And for that purpose, we rely on a data set comprising information about genes of which the classes you already know. We are using data from the GeneAge database about aging-related genes of 4 model organisms, which are the mouse, the fruit fly, the roundworm, and the baker's yeast. And additionally, we are using data from the string database of protein-protein interactions, or PPI for short. And to summarize that concept, genes encode proteins, and each protein may interact with other proteins inside the cell of an organism, and that may have some influence in the aging process of that organism. So in our data sets, a PPI feature indicates whether or not a protein encoded by the considered gene interacts with some other specific protein. However, the available data about PPI is uncertain, which means we do not have a true or false value indicating whether or not that specific interaction occurs or not. Instead, we have confidence scores of the occurrence of that specific interaction, which translates into a probability distribution. For instance, we could have for a specific gene PPI pair a confidence score that tells us the probability of occurrence of that interaction, which is represented by the value true, is 0.3, which implies the probability of the value false is 0.7, and that forms a probability distribution on this binary domain. So far, I've talked about the problem and the data. So now let me talk about techniques. First, I'm going to use this small example to describe a decision tree classifier. It is a tree structure model in which we evaluate a feature value, one specific feature value at each internal node. And if the value of that feature is false, one comment, and in this example, as in our data sets, we only have true or false features. So if the value for a feature we are evaluating is false, then we proceed to the left child node. Otherwise, we proceed to the right child node. And this process goes on until we reach a leaf node, which represents the class prediction itself. As illustrated by this path from the root node to a leaf node. And we can build such a model by starting from the root node with all the training instances. Then we need to choose the best feature to split the instances according to some criteria. So then if the instance that have the value false for the chosen feature are copied into the left child node, and the other instances are copied into the right child node. And this process is repeated until we have nodes where all the instances are of the same class, which will become the leaf nodes. Now, a random forest classifier is an ensemble of decision trees, distinct decision trees, obtained through random variations in the tree building process. Each tree is built from a set of instances randomly sampled from the original training set with replacement, which is called Bootstrap. And additionally, the the best splitting feature for each node is chosen from a random subset of all features. So these are the two random components of the random forest. And the predicted class in this model is the one with the majority of votes among all trees. And this improves predictive accuracy and prevents overfitting of the model to the training data in comparison to the use of one single decision tree. Here I list some strategies used to handle uncertain data. And the simple one is simply selecting the expected values, which are those values with the highest probabilities in the corresponding distributions. And there actually means ignoring information on uncertainty. Another one is to randomly sample values before each tree generation, which means each uncertain feature value is replaced by a value randomly sampled from the corresponding probability distribution. And finally, to conclude, here are some novel strategies we've been exploring, and they correspond to the random components of the random forest. The first is biased bootstrap, where the probability for each instance to be sampled is based on an uncertainty degree computed for that instance. And the second one is a biased splitting, where the probability for a feature to be considered to split the node, the instances of a node, is based on an uncertainty degree computed for that feature. Well, this is a work in progress, and I still do not have any results to show, but we expect these novel strategies shall improve the performance of random forests in the context of classification of aging-related genes. Thank you, everyone. And if you have any questions, I'll do my best to answer them.
Okay, Marcelo, thank you very much. I would like to ask you to emphasize which of these strategies are yours and which ones are from the literature.
Sure. So these are some examples of strategies found in the literature to handle uncertain data. And these two are the novel strategies we are proposing in this project. So these one are the novel ones.
Okay, and could you also explain which kind of tools and languages are you using to implement your ideas?
Sure. Currently, we've been working with Python, specifically with the scikit-learn, which is mostly Python, but we also use some C and C++ libraries through the Python extensions. But we are not yet closer at this. We still consider some other tools, but currently that's it.
Okay, Marcelo, thank you very much for your presentation. And now I will call Professor Angel Sanchez from Universidad Rey Juan Carlos, Spain, to present his work entitled, just a moment, entitled Recent Work on Document Image Analysis at URJC. Yes, Angel, please, you can start. Your mic is mute, okay?
Your audio is muted, Angel. You can enable it at the
It's
bottom
okay?
left corner. Okay, yes.
Okay, now. I will present some recent work of my group on document image analysis. This presentation is a bit far from your work in medical informatics. So perhaps the motivation is to show some words in this field in order to get some insight to people and maybe share some research collaboration. My university is in Madrid, and we work in our group in the fields of computer vision and biometrics with application on text, handwritten text recognition and signatures verification. What I have done is to show you some slides of recent work related to handwritten signature problems we have published. And at the end, I present an idea that I have for a possible handwritten application to the field of digital healthcare. First, the first problem is how using offline handwriting to predict the gender and handedness of the person. The second problem is handwritten recognition using deep learning, long short-term memories. I added a part on anonymization of documents. If I have no time, I can skip it. Then I will speak about signature verification, specifically the detection of forgeries. And finally, this part relates to how to detect or to relate the effects on skilled forgeries relate with some possible illness like Parkinson or Alzheimer. Well, the problem of gender and handedness prediction use handwritten text, annotate the handwritten text with the information in order to determine the gender of the person, man versus woman, the handedness, right-handed versus left-handed, or the combined problem. Right-handed man, left-handed man, right-handed woman, left-handed woman. For solving this problem, we use deep learning, in particular some type of convolutional neural networks, VGG, and apply to different data sets, some data set with Latin alphabet, the AIM data set, and other with Arabic script. Here you have some examples of text, handwritten text. The first one, in the left part in English, the right part in Arabic, and we have the different situation explained. Right-handed man, left-handed man, right-handed woman, left-handed woman. We all have the intuition, for example, that the handwriting of a woman is more regular, more clear in general, and Also, with respect to left-handed people, they write the characters, the letters in a different, perhaps in a different way. So we have to investigate in this problem. We use this data set, divide the data set is organized in annotated sentences. We split these sentences into words or blocks, and with these blocks of the same size, we train convolutional neural networks and types with using also data augmentation to create a synthetic test with some variation respect with the orientation and the scaling of the words, etc. And after training the model, we consider that a sentence is correctly predicted with most of the blocks in a test sentence correspond to a given type. For example, if we split a sentence in 8 blocks, if we have 6 blocks where the network says it's a man and 2 for a woman, then we classify the sentence as a man. And the same for right-handed and left-handed, and the combined problem. Here we have some results for the IAM database in Latin script and for the CAT database, and compare the results in the literature with others works. The problems in the case of man woman, we have the balanced classes, but in the case of handedness, approximately only 10% of the population is left-handed and the rest is right-handed. So we have an unbalance of the classes, and this is reflected in the results. Here I show only the combined results, but you see that the results are a bit worse where the left-handed is part. Okay, this is a resume of the work. The other work I want to present you is related with recognition of handwritten continuous tests. Without continuous mean we don't perform any segmentation, and offline means the text is first writing and then it's scanning, not is obtained using some device, some electronic device like a Wacom tablet. Okay. The idea is we combine a convolutional neural network with a seek-to-seek network, which has 2 parts, an encoder and a decoder part, which are long short-term memories, and also include an attention mechanism, and we use this architecture to recognize continuous tests. Okay, we have used 2 data sets. IAM, the same that in the first paper, and RHYMES, which is other data set with tests in French language. Okay, I will show this one. The algorithm is first we split the words we want to recognize in patches, which are are overlapped patches, and we use a convolutional network to extract features which are input to an encoder which is this long short-term memory encoder. And we train this model using also attention mechanism, which tries to predict a character in the decoding phase using the information of previous character and the whole word also. This is the architecture of the model. The test is first pre-processed, and for example, the slant and skew are corrected after splitting the sentences into patches. Then here we have patches corresponding to a word, which can be overlapped. And we train the model to predict words based to predict letters better, considering the image of the words and the previous components letter predicted in the word. Here I present some results. Where is the word at the word error rate, and character error rate for both database, and the first table corresponds the solution without using the results without using any dictionary, which is the most difficult case. In the second case, we use an standard dictionary, and with this dictionary, the errors at the word and character level decrease. And the last table shows the result using as dictionary only the text lexicon. The idea is when the prediction of a word is by the network is not in the dictionary, we use some distance measure in order to approximate the word to the closest word in the dictionary. Okay. Here I showed the results of errors at the word level in function of the word length. Without using dictionary, as the word length increase, the errors increase for both databases. The same does not happen using a dictionary. For example, the text lexicon. In that case, the errors don't depend on the length of the word, but on the numbers of words of a given length in the dictionary. More. Okay. How is the time now? I mean, it's how much time do I have for the rest of the presentation?
You can go on. Don't worry about that. We have time.
Okay. The next word is related to anonymization of documents. We want to locate sensible information in documents like invoices, for example, the personal information, the names, the ID numbers, social security numbers, etc. And we want from a given document to produce an image that resembles as much as possible to the original one with the sensible information anonymized. That is the idea. Anonymize the sensible text and produce a transformed documents image, which is more similar to the original one with respect to the letter type, with the fonts and some information. We have applied this our experiments to invoices. First, we use an OCR engine, Tesseract, to anonymize the sensible text, and we use dictionary and regular expression in order to detect this specific information we have and structure. Regarding text anonymization techniques, we use text suppression, tagging, which consists in substituting, for example, the name of a person for the word name, random substitution, which substitutes a name for other name of other person, for example, and text generalization, which is similar to tagging, but more general. We use a convolutional neural network to learn the font types and also some Arial, Times Roman, Courier, etc., and style variants like italic and bold. Okay. This is an algorithm of how we perform the process. We digitize the documents, apply OCR. After applying the OCR, we detect the position where this sensible information is located. We recognize them and anonymize using the rules I explained before, like tagging, etc. And then we from the documents we train a convolutional neural network to learn the font and styles, and finally we combine the anonymized information, new anonymized information with the information in the document, and place this, as we know by the TCR where this information is located, we place in the document and generate an anonymized image document. Okay, the structure of the networks, and then this is the output is very small, but this is an electric company invoice, and we determine the components and make the substitution. And here is the results in the small part. The sensible fields are anonymized. Okay, and the last work I want to show you is related with signature verification offline to detect random forgeries. We have used in all works I have presented, we use deep learning, different types of neural networks. In this case, we have used CMS neural networks for detect random forgeries. CMS neural networks are networks which has two twins which share weights, and when trained, the weights are updated in both teams of twins of the networks. Okay. One specific part of this work is that we want to detect random forgeries. Random forgeries are those ones which are not very elaborate, where in this case the person the writer does not know how the signature of the signer is. So he tried to imagine the signature and write something. For example, he knows the name but not the signature. Okay, we evaluate different components in the twins of the CMS networks, and we test with augmented the information of the data set with these shape signatures and test with different databases. The problem of verification is to determine given two signatures, a model signature and a test signature, if both belong to the same person or not. If the test signature is authentic or is a forgery. We train this CMS network. Is a supervised training process. Okay. Here is described the architecture and the most important the solution. The most important part is the synthetic signature generation, with helps to detect the random forgeries. I will skip this step of generating random synthetic signatures, but you can, these random synthetic signatures are generated using some geometric primitives like lines, triangles, cycloids, circles, etc., which are combined properly and with a different parameterization. For example, here we have two synthetic signatures which are generated with similar parameters. There are a slight variation between signatures, and on the right one, this is generated with a different use of steps and primitives. Okay, the most important part in our model is the architecture of the solution, which is called CMS convolutional insertion neural network. The most important part is the insertion module, which allow to perform convolutions in parallel with different masks and concatenate the result. With these steps have improved our results. Okay, here I show the effect of using synthetic signatures, including the TS3 is this synthetic generation of random signatures to detect random forgeries. This worked very well, and the error rate was greatly reduced. In this experiment, we tested different configuration of the twins modules, and with our proposal, we reduced the number of parameters. And these are the results corresponding to the experiments using different data sets. In two of the experimented data sets, we achieved the best result compared to others' work. And next, I will finish with a possible idea for how handwritten signature can be applied to these healthcare problems. It is known that healthy people write automatically and fluently, producing smooth handwriting strokes. That is when handwriting, also when signing. In general, neurodegenerative disease influence the handwriting, and also the signature, for example, producing tremors in parts of the handwriting. Analyzing the handwriting of sick or elderly people could help us to diagnostic some situations, impairments like Parkinson, for example. For the case of offline, I have not seen handwritten database or signature database to investigate this problem. Our idea is to relate our experience using deep neural networks, in particular CMS networks. We have also used not only for random, but also for to detect skilled forgeries. And we can detect these forgeries. This knowledge to detect falsification or forgeries could be adapted to detect symptoms of this neuromotor related disease. We can analyze some features like tremors, abrupt change in the direction of the stroke, pen patching when one retouches some parts of the characters, pen skipping, pause when handwriting or signing, and change in some letter forms. For example, these are some forgeries. In these forgeries, we can, when one is making a forgery of a signature of someone, this person does not perfect the signature he or she is imitating. So there is some patching, some pen patching on some irregular parts which can be detected in the signature. I show here a signature for a person 95-year-old with some mild Parkinson disease, and we can observe that at the beginning of the signature we have this pen patching effect, and also tremors in some parts, in the center parts and in the strokes. We can make the hypothesis that perhaps it's possible to find similarities in the techniques used to detect these forgeries and to detect this age and neuromotor related disease when analyzing both handwritten signatures and text. We have not worked in this problem, but I consider interest to do research in it. That's all. Thank you very much. Do you have questions?
Yes, Professor Angel. Thank you very much for your talk, and congratulations for your proposals and results. They are very nice. We have 3 questions. The first one is from Aline, Professor Aline from UF. The question is, do you cope with special characters like tilde in languages like Portuguese and Spanish, but not English? A student of mine works with this task in Portuguese, and we have to handle those.
You mean special characters?
Yes, like tilde is one.
Tildes. Okay. In the, you mean in signatures or in text? For example, in one of the experiments of word recognition, we use the database RIMS, which has text in French. In French, you have accents, also circumflex accents. I don't know if this is exactly the question.
Okay, Aline is not here, so I don't know if she can make it clear, but I will go to the next question. Also, the issue with gender. Is there a physiological reason for the difference in handwritten between genders, or this is related to cultural and historical reasons?
I don't know. It's a very interesting question, but why is interesting this problem? Why do I start investigating this problem? When I correct exams in paper, I noticed that the handwriting was different between man and woman. I can hide the name of the person, and I play with a colleague to guess if this exam is from a boy or a girl. And I can many times when you are trying it, you can guess. And I try to do the same problem and discover that some authors have also worked in the same problem. I don't know if this classification or prediction have any relationship with health. Do you find any application with to health?
Okay, Aline has just written here in the chat that she is talking about. Can you read the chat? The question is both in texts and signatures.
I can see the chat. Okay. Perhaps if I return to the other, if you give me the questions, it's better.
She is. We have A with accent, I with accent.
Mm-hmm.
She would like to know if you handle this in text and also in signatures.
In text is possible, no problem. You train your models and you learn to predict. For example, if you use a target language, you can train the models, this sec-to-sec model, to learn words with accents. You have to get enough samples, enough labeled word to train the model, but no problem the accents.
Okay, we have another question from Professor Leticia from UF. I think this question is also very difficult, but it's a very interesting question. In the same vein as Aline's question, is there an influence on the results for gender identity or sexual orientation?
I don't understand well the question. Could you explain me?
Yes,
I understand
the identity of gender or the sexual orientation, if these features may affect the handwriting and this could influence the result. Could you identify the gender identity or the sexual orientation by the handwriting, for example?
The system is based in data, in massive use of data. if I don't understand well, if I understand well the question, I'm not sure if it's there is rules to determine the how. I don't know. It's difficult to understand.
Yes,
this.
yes, it's a difficult question, but it's very interesting. I suppose that instead of having the class, the gender could be the gender identity or the sexual orientation. So we could evaluate if the handwriting has a correlance.
Okay. I understand now.
Is related to sexual orientation or gender identity. Okay.
We learn to predict, but with these models, but how you can find also some situations where the prediction, when you see the image of the test and the labels seem that don't match, but in some case you can don't correspond. For example, you can in some case the handwriting of a woman is more men-like. Not always is possible to establish this correlation.
Okay. Thank you very much, Professor Angel. I think there is
You're welcome.
Question. Yes, thank you very much.
Thank you.
Now, I ask Adriel to share his presentation.
Everyone.
We're going to listen to Adriel. Adriel Araújo is a PhD student from UF. And the title of his presentation is Monitoring Breast Cancer Treatment Using Thermographic Time Series. Okay, thank you, Adriel. You can go.
Exactly, thank you for your presentation, Faustino. So now we'll have a little talk about our current research that intends to monitor breast cancer treatment using thermographic time series. And in this conversation, we'll cover some important points related to breast cancer and its relation with infrared examinations, thermographic examinations, pointing out some traditional problems of this field and our current our proposed methodology to fill some gaps on this field, and also as well presenting our results and conclusions in this step. The first important point that we need to mention here is the huge incidence of breast cancer. This kind of cancer represents almost 25% of all kinds of cancer in the world. In number, it's almost 1.7 million of new cases a year. So definitely it's a huge incidence. And another important characteristic of breast cancer is that it alters the thermal pattern, the human thermal pattern. And it's in that point that appears the thermographic examination, because it's a kind of examination that can detect changes in thermal pattern. Here we have an example of a thermal examination, a thermographic examination, where the patient has a tumor on the right breast side. And we can see, just looking for this image, that this side of the breast has a different pattern, in this case, a different thermal pattern. And it's also interesting to mention that it's a totally non-invasive technique, and also widely used in screening researchers and diagnosis researchers, and not just in breast cancer, but also in other fields. But few studies are devoted to use this kind of investigation, this kind of examination to follow up breast cancer treatment. And we need it. We need to provide for physicians a solution that will help them to understand how the breast cancer treatment is going on without an invasive technique. And to tackle this problem, we are proposing here a methodology to monitor this evolution of breast cancer treatment using thermographic time series. And our approach is based in 4 steps. In the first one, we pre-process the examinations where we will obtain the region of interest. And here, our region of interest is the breast region, the breast region with tumor. And after we obtain the region of interest, we clusterize all those regions, all those images, to obtain inside of this region of interest, the area with whole test points. Because in here, in this image, this area is represented by the white color. Because we intend to use this region to compute features and build time features, time series from this area, from this point, the thermal points on this area. And finally, summarizing these features, compute this time series, computing some measures that will help us to evaluate the breast cancer treatment. And on this methodology, for each patient, we are using 2 thermographic examinations, one before the treatment, called visit 1, and another one after the treatment, called here visit 2. And also for those images, we are computing 2 statistical features from these selected clusters, that is average temperature and maximum temperature, and building time series from these features. And finally, summarizing this time series on 2 measures called here variation, that is the difference between the first item in this time series and the last item, and the median variation, that is the average variation of this whole time series. Here is the data that we are using in this step of the work, 12 patients with 2 visits, and we can see on this table that all those patients, there's different locations, different tumor locations, as we can see in the first two columns, and different tumor sizes, as we can see in the last 2 columns. All those patients are patients that use the best by the neoadjuvant treatment, that is the treatment that happens before a surgical intervention, the chemotherapy, for example. And I call your attention here for patient 3, that unfortunately, after the treatment, the tumor size increased after the treatment. So considering these points, let's see some results that we achieved using this methodology. And the first interesting and important point that I want to share with you are the results that we obtained on the clusterization process. Here, we clusterize all regions of interest of our 12 patients. We are showing here 1 image for each patient. And we can, our intent here is check if the whole test cluster also matches with the tumor location. And it happens. In fact, it happens. For example, let's start with the patient 1. Patient 1 has the tumor location on the upper quadrant on the breasts. And these quadrants are located on the upper region of the breast. And the highest cluster that is highlighted in white color here, it's also presented in the same location. It means the same tumor location on the breast. And it also happened not just for patient 1, but for all patients that we are using on this work. So it's interesting because these results allows us to use this thermal data, the thermal data on these points to compute our features and build time series from these features. And here, I also sharing with you another result from 1 time series, the average time series, comparing the result from between visit 1 and visit 2. Here, the orange color represent the measures, these 2 measures computed from time series on visit 1, and the blue color represent the measures computed from the time series on visit 2. And we can see here that for most part of our patients, that the thermal evolution follows the clinical evolution. For example, the patient 12, that is the first one, top bottom here, decrease the tumor size on the second visit. And we also can see for both mysteries that this value also decrease, also present a lower value, also a lower number on this visit too. And we also can see this for others, from the others patients in this study. And remember, when I call your attention for patient 3 that unfortunately increased the tumor size on visit 2, we also can see this result here. We also can see the situation here that this patient, the measure is computed from the time series on visit 2 for this patient also present higher values than the values obtained on visit 1. So again, following the clinical evolution. And for all those 12 patients, in just one case, the results walked in an opposite way of the clinical evolution. That is the patient 2 that decreased the treatment, decreased the tumor size, sorry, and these measures are presenting our results in a different direction. And we also can confirm it here when we are comparing the clinical evolution versus thermal evolutions from each time series, of course, for each patient. And just one, the patient 2 walks in a different way. But for example, the patient 1 reduced the tumor size, something about 30%. And we also can see a similar reduction in walking in the same direction from those time series that we computed from this patient. Patient 3, for example, that unfortunately, again, increased the tumor size, we also can see this increase, these higher values computed from these measures on those time series. And similar for other patients. For some of them, these green cells, we have very similar results. For others, not so similar, but also walking in the same direction, representing an evolution in the same way of clinical evolution. And just for patient 2, we didn't have a good match. But these results are interesting because this study shows us that this methodology is promising for monitoring breast cancer treatment using the thermal data from the whole test the tumor whole test area. And suggesting us that use tomographic time series, it's a good way, it's a good alternative to indicate tumor evolution under different measures. And in the next steps of this work, we are planning to use more tomographic data from more patients and also conduct studies with more robust time series, compute more time series, and from those time series, this time series also compute more measures, different measures. And also not just to build a hybrid approach, not just using unsupervised learning to clusterize, but also using supervised learning algorithms to estimate, for example, the tumor size, the tumor evolution on each visit of patient. So this is our future steps. It was a short talk, and thank you everyone for your attention. If you have any question, I will do my best to answer you.
Thank you very much, Adriel. Very interesting problem and solutions. And I'm very curious about how did you use the k-means to identify the regions? It was not clear for me. The use of clusterization to identify the
Okay, good question, Cristiano. Well, in this step, our goal was to form clusters on the region of interest. Here are the region of interest that represent each breast side with tumor from each patient. And from this region of interest, our goal was to select it, to understand what is the whole test point on this region, to use them to to compute our features and build our time series. So we selected 9 clusters. This number, 9 clusters, was decided by empirical studies and also comparing with other results from other researchers in our group. Because in our group, we are already working with breast cancer and this kind of examination, but not just for follow-up the treatment. But recent studies are to screening and diagnosis. So combining empirical studies and our recent results, we selected 9 clusters. In this step of this work, we are just using the higher temperature cluster. It means from these 9 clusters, we are selecting the first cluster that presents the higher temperature on those points. But we also intend to use not just the first point, the whole test cluster, but for example, in those images, not just the cluster represented by the white color, but those other clusters closer to the white, for example, the pink color and red color, the first, second, and third. It's also included in our next steps.
Okay, it's clearer now for me. But another question regarding the clusterization. What was the data set that was input for this clustering processing? Okay, which are the features of this data set?
Good point, good point.
To allow the clusterization to organize the information among clusters, I would like to know which are the features that represent each cell or each part of the image. What are the features?
Okay. Well, regarding the whole data set, we built this data set in a partnership with a hospital, and we made some acquisitions to obtain this thermographic times image, because we already have a breast image, thermographic times image, but not on patients that are undergoing treatment. And related to the clusterization process, we are using the whole raw image as input of the breast of the clusterization, as input for the clusterization algorithm. And the output of this process is just labeled for each point in the matrix of the Y. So this point represents label 1, that it's the whole test group. This point is another point, label 2, and until we achieve the label 9.
Okay, Adriel, but which are the features of each point? Now I understood that you organize the points, characterize the regions. And what are the features with the information, the data about each point?
Okay, I got your questions. Well, we are using the feature are temperature values, and from those groups, all those temperature values that we collected from their thermographic examinations, we are computing 2 features that are statistical features. That is the maximum temperature of the whole cluster, and the median, the average temperature of the whole cluster.
Okay.
Are those 2 features? And I think, and I'm not sure if I respond you, if I answer your question, appropriate.
Nice. Okay, we could discuss it later.
Okay.
Okay, thank you very much, Adriel, for your presentation. Very nice work. Congratulations.
Okay. Thank you.
I have a question for Adriel.
Okay.
Regarding that patient, I think it was patient 2 that you showed that the thermographic results in the opposite direction. Do you think it might be related to the type of cancer cells that is involved with the patient? Maybe a different kind of tumors or cancers may not be good to detect using the thermographic technique?
A very good question. Meters, right? well, we did not perform a deeply investigation on this in this case yet, but those are some points that we are investigating for. All those patients, in fact, there's just two kinds of cancers. That is HAR positive and triple negative. So there's no big difference in the kind of breast cancer from those patients. All those there's just the same, just two kinds of breast cancer. So probably it's not a point, but we need to investigate it deeply to respond to you in a more concrete way.
Okay, thanks.
Okay, you're welcome.
Thank you very much. Adriel, now I will call, just a moment.
I think now it's Isabel.
Okay, Mirtz, you conduct now.
Okay,
yes.
Thanks.
Okay. Thank you very much. Thank you very much.
So now it's a pleasure to invite Isabel to talk here with us. So Isabel is a professor from the Biomedical Institute, from the same lab that me and Leticia work, at the Laboratory of Neurophysiology of Behavior from the Federal Fluminense University. And today she will talk about her work that she conducted during her postdoc at University College London. During her postdoc, she worked at the Computer Science Department in the lab of Professor Janaína Mourão Miranda. And so Isabel will talk today about neuroimaging data from multiple sources in Pronto, version 3, spatial temporal patterns of face processing. So welcome, Isabel.
So I'm going to share my screen. Just a minute. Are you seeing it?
Yes.
So thank you for the invitation. As has been said, my name is Isabel David. I'm an associate professor at Federal Fluminense University in the Department of Physiology. And today I'm going to present the work entitled Neuroimaging Data from Multiple Sources in Pronto versus 3, Spatial Temporal Patterns of Face Processing. And as has been told, this study was developed during my postdoc at University College London in the lab that's headed by Janaína Mourão Miranda. So the study deals with an aspect of human social intelligence, that is the ability in recognizing faces. We are constantly recognizing faces countless times a day, and most of us take for granted. Face recognition seems to be super efficient and fast, particularly if the faces are familiar to you. For instance, look at these faces, you immediately recognize the features related to the faces on the left. You have no difficulty in recognizing them. So use the information from faces to recognize individual human. It's not the only thing we do, but it's a very important function of processing faces filters. Differences in processing familiar and unfamiliar faces are particularly remarkable given they are both face stimuli, and even though they share the same configuration of features, familiarity seems to promote an improvement in identity recognition based on past experiences. And given that famous and unfamiliar faces are both faces, but promote different responses, it would be interesting to observe the similarities and differences in brain activity involved in processing famous and unfamiliar faces. Despite the evidence that brain processes for the perception of familiar and unfamiliar faces are different, there is ongoing controversy regarding the extent to which familiarity influences faces processing. The processing of faces is complex and involves extensive and diverse areas of the brain, like the occipital-temporal cortex and beyond. And these distributed face neural areas may not work in isolation, but they operate in an integrated fashion as an interconnected face processing network. And interesting is that this face information may be represented also at different times, suggesting that this face processing network is also temporally distributed. So face processing may involve networks of regions that changes over time. Well, we were interested in exploring the spatial temporal dynamics of brain activity related to face processing. Fmri, EEG, and MEG are neuroimaging modalities that have complementary advantage with regard to the spatial and temporal resolution. So we used a publicly available multimodal data set containing EEG, MEG, and Fmri neuroimaging data from 16 participants who undertook multiple runs of a simple task performed on a large number of images containing faces, unfamiliar and famous, and also known faces, scrambled stimuli that worked as controls. Now I move on the multimodal machine learning framework that we applied. We used the pattern recognition methods. The goal of pattern recognition analysis to find patterns, regularities in the data that can be used to make predictions. And pattern recognition can be successfully achieved by using machine learning approach. In this study, we used the multiple kernel learning classification models to learn the contribution of different brain regions and time windows to discriminate between faces versus non-faces stimuli. The multiple kernel learning refers to a set of machine learning methods in which kernels can be considered a linear combination of basis kernels, and the MKL machine estimates the contribution of each kernel for the prediction. We can combine different sources of information as different kernels. So it provides a very nice framework for integrate different types of data for the prediction, or also to build multimodal predictive models. This is an approach that is implemented in the pattern recognition for neuroimaging toolbox, that is a software based on pattern recognition techniques for the analysis of neuroimaging data, and that was developed by our research group in UCL. Here is the link to access this toolbox, particularly in Pronto versus tree. It's possible to do this multimodal combination. We implemented two models in Pronto versus tree. Model 1 was trained to discriminate between spatial temporal patterns of brain activation to unfamiliar faces versus scrambled stimuli. And model 2 was trained to discriminate between spatial temporal patterns of brain activation to famous faces versus scrambled stimuli. Now I move on to explain better the multimodal kernel learning framework that was applied in our study. So machine learning algorithms build a mathematical model based on training data in order to make predictions of decisions without being explicitly programmed to do so. So the framework consists in two phases, the training phase and the test phase. And during the training phase, we give the training examples and the labels as input to the machine learning algorithms. Here, the input was the neuroimaging data from 16 participants, and this neuroimaging data was from different neuroimage techniques such as fMRI, EEG, MEG, as I told you before. And the data from each technique was considered a different modality. The files input were the beta images by subjects in the case of Fmri, and the average trace per subject in the case of EEG and MEG. The labels were the different conditions, that is familiar faces and scrambled stimuli in the case of model 1, and famous faces and scrambled stimuli in the case of model 2. We built different kernels for technique, selecting features according to previous information about brain anatomy in the case of Fmri and temporal processing in the case of EEG MEG. And the features were stored and further used to enable building the kernel weights. For Fmri, linear kernels were built from regional patterns of activity based on the anatomical labeling atlas. And for EEG and MEG, linear kernels were built from non-overlapping segments of 100 milliseconds length extracted from the interval between stimulus onset and 800 milliseconds. So multiple kernel learning machine then learn a predictive function that discriminates between patterns of brain activation to faces versus non-faces. And all the kernels from different modalities are integrated into the same model and analysis. They are normalized to compensate for the fact that the different modalities have different numbers of features, and also mean-centered using standard operation in Pronto versus tree. And the MKL model simultaneously learns the contribution of each region, that is the region weights, and of each time window, that is the time windows weights, and also the contribution of each features within each region, that is the voxel weights. And finally, the contribution of each features within each time window, that is the weight for time points across channels. The contribution of each modality then is computed adding all kernel weights for the specific modality. So during the training phase, the outcome is a predictive function that can then be used during the second phase that is named as the test phase to make the predictions. In this phase, given a new example, we can predict the labels, the conditions, and the data were split in test and training, use a four-fold cross-validation on subjects out. And two metrics were used to evaluate the model performance, the balance accuracy, and the area under the receiver operating characteristic curve. And the statistical significance of the classification measures was determined using permutation testing. We addressed three main questions about how face familiarity influences face processing. The first question was, face familiarity plays a role in the discriminability between spatial temporal patterns of brain activity faces versus non-faces stimuli. The other question was, which patterns of brain activity, temporal or spatial, contribute more to the model discriminating between patterns of brain activity faces, famous or unfamiliar, versus non-faces stimuli. And the last question was, which specific brain regions and time windows contribute to the model discriminating between patterns of brain activity faces, famous or unfamiliar, versus non-faces stimuli. So now moving on to the results, we were interested if accuracy for discriminating between patterns of brain activity faces versus non-faces stimuli would depend on facial familiarity. And we found a higher performance of the pattern classification model for discriminating between patterns of brain activity famous faces versus scrambled stimuli than for discriminating between patterns of brain activity unfamiliar faces versus scrambled stimuli. It has been suggested that familiar faces are recognized more robustly and quicker than unfamiliar faces. Thus, specific characteristics of famous faces may have generated in our study spatial temporal patterns of brain activities that were highly informative to discriminate them from scrambled stimuli. We also aimed to identify which patterns of brain activity, temporal or spatial, contributed more to discriminate faces, unfamiliar or famous, versus non-faces stimuli. And we addressed this issue by showing the relative contribution of patterns from high spatial, Fmri, for instance, and high temporal, e.g. NAG, resolution techniques to the predictive function. We found that spatial patterns of brain activity contributed more to discriminate famous faces versus scrambled stimuli. So faces familiarity also influences the relative contribution of patterns from high spatial and high temporal resolution techniques to the model, discriminating between patterns of brain activity faces versus non-faces stimuli. It's likely that multiple regions would be simultaneously activated in parallel during the processing of famous faces. So spatial patterns from these regions would be providing a higher contribution to the classification model than temporal patterns from specific time windows. Finally, we were also interested in determining which regions and time windows contribute to discriminate between patterns of brain activity faces, famous or unfamiliar, versus non-faces stimuli. Starting with Fmri results, some brain regions previously described as important to faces processing, such as fusiform gyrus, insular cortex, hippocampus, and gyrus rectus, were identified by both models, discriminating between patterns of brain activity to unfamiliar or famous faces versus scrambled stimuli, regardless of face familiarity. However, the occipital gyrus were uniquely identified by the model, discriminating between patterns of brain activity on familiar faces versus scrambled stimuli, while the temporal pole, left amygdala, right middle frontal gyrus were uniquely identified by the model, discriminating between patterns of brain activity of famous faces versus scrambled stimuli. It has been proposed that the face processing network can be divided into a core system that is engaged in processing the visual aspects of faces, and also in a standard system that acts in concert with the core system in order to obtain different types of additional information from faces, such as retrieval of person knowledge, emotions, eye gaze, and intentions. The right inferior occipital gyrus is a region from the core system, and the areas from the that is on the right are from the extended system. And our results are in line with the previous works, showing that unfamiliar faces would recruit regions from the core system with more intensity. On the other hand, familiar faces would recruit regions from standard system with more intensity. It's important to mention that these areas on the right were reported to be directly or indirectly related to familiarity processing. So it makes sense that they were identified by the model, discriminating between patterns of brain activity to famous faces versus scrambled stimuli, and were not identified by the model, discriminating between patterns of brain activity on familiar faces versus scrambled stimuli. Now, regarding the EEG results, the time window between 100 and 199 milliseconds highly contributed to discriminating between patterns of brain activity to unfamiliar faces versus scrambled stimuli. This is the time window in which the event-related components, named in 170 components, it's when this component occurs. This component is a well-known component involved in faces recognition. And what is important to mention about this component is that it has been related to the core system, that is, to the processing of the visual aspects of faces. As I mentioned before, the core system seems to contribute more to the processing of unfamiliar faces. In line with this assumption, we found that the time windows that include the N170 component highly contributed to the model discriminating between patterns of brain activity to unfamiliar faces versus scrambled stimuli. However, this time window was not identified as relevant for classification by the model discriminating between patterns of brain activity to famous faces versus scrambled stimuli. Finally, regarding the MAG results, the time window between 400 and 499 milliseconds was only identified by the model discriminating between patterns of brain activity to famous faces versus scrambled stimuli. This time window has been specifically reported to be important for the processing of familiar faces. One more time, ratifying the important contribution of the standard system in processing faces familiarity. As conclusions, we have that faces familiarity plays a role in the discriminability between spatial temporal patterns of brain activity to faces versus non-faces stimuli. Processing famous faces may involve the activation of multiple brain regions in parallel. Processing famous and unfamiliar faces may involve similar but yet different networks and dynamics. And finally, the multimodal machine learning framework applied here provides a new approach to uncover fine-grained characterization of the spatial temporal dynamics underlying faces processing. Thank you very much for the invitation and your attention.
Thanks, Isabel, for the excellent talk. Let me see if you have questions here. I have, in fact, two questions. First of all, I think it's kind of just to think about why amygdala was not so important to discriminate the unfamiliar face versus scrambled face, considering that the literature shows that amygdala is always so active when you have face in an experiment. Do you have an idea why it was not an important area to discriminate face?
Oh, it's included in discriminate faces. I only highlight the areas that were important to discriminate on familiar and familiar faces, but actually it's not on the top of the list, but it's there actually.
So it was important too. Okay.
Yes, we have a limited time, but if I put all the complete list, of course the amygdala is there, but it's not on the top. It's not the most important area. Actually, we were not comparing directly unfamiliar and famous faces. We were doing different models, not comparing, but in the classification, we used to the prediction, the familiar faces versus scrambled stimuli. And in this case, we are not highlighting the things that are important exactly to discriminate familiar and unfamiliar. The reason we have done that is because there are a lot of information in literature about processing unfamiliar and unfamiliar faces, but there is nothing about how we can discriminate, if familiarity is important, to discriminate no faces from faces. This is the thing that we are interested in understand better. So we are very fast in recognizing faces, but familiarity do what in terms to this discrimination.
Okay. And could you please comment a little bit about other applications of Pronto? Maybe you talked about neuroscience application, but about clinical data or clinical application.
Yeah, it's a very important question because I have done a basic research, but actually Pronto Toolbox has been applied in studies in the psychiatry field. Some of those studies were developed by our research group. And the labels that are used for classification, they can be instead of different mental states, like the ones that are listed by faces or no faces or other stimuli. The labels can be subjects, like controls and patients. It's one thing that we can do. But Pronto also allows, that is very interesting, the application of regression models that may also help to find brain markers that are predictive of anxiety, depression, and other pathological psychiatric condition.
Okay, thanks, Isabel. We will have some minutes at the end of the session, and maybe we have new questions because we have a short delay between Zoom and YouTube. Sometimes the questions come after the end of the session, so maybe we'll come back later.
Sure.
Thank you, again.
Yeah, I think Ian Plastino would like to make questions.
Oh, okay. Oh, I didn't. Sorry. Okay.
So can I start?
Yes, Deborah, please.
Well, so Isabel, thank you for your presentation. Very nice work.
I have a question. What about people with prosopagnosia? Have you tested with those people we have the non-ability to recognize familiar faces?
Yeah, it's a very nice question. This is a new approach in Pronto, the multimodal machine learning approach. So we use it publicly data, but actually I think that the next step would be do a very nice well-designed work and try to understand, use this approach in other designers. In one of them that would be very interested as a next step would be understand better prosopagnosia or things like that. I think it would be a really nice approach to do in the future. Thank you for the suggestion.
Okay, Isabel, and my question is, you said that you have used this multimodal machine learning approach. I don't know if I understood it well, but I would like to know if you have combined different machine learning algorithms in order to generate your results, or you have used different kind of information, but with the same machine learning algorithm.
You use different kinds of information. You build kernels from different techniques and combine the kernels and normalize all the information, because you are joining information from different features, and the number of features are different. So it's a very interesting approach because you can combine different techniques like fMRI and use all this information to make predictions. So it's very nice to, and you can use classification models and regression, and it's very nice. So you add much more information to do the predictions in Pronto versus 3.
Okay, thank you.
Hi, Isabel. Thank you for your talk. Very interesting work. I'm just curious about the size of the data sets used in the experiments and if they are class balanced, the distribution of the class, how the class distributed in these data sets.
Yes, it's distributed in the 2 groups. It's balanced. It's actually from the SPN group. So it's a data set that is available for the SPM toolbox that's classically used for the analysis of fMRI. It's a group from UCL too that developed this toolbox. So they were there in the UCL. That was very useful because I could talk to them about the data. It's nice, and it's well balanced. I was very worried about the number of females and males, and if people were smiling in both conditions, and everything was balanced. It was a very nice, and they have a lot of trials. It was a very good thing. Although it's 16 participants, but they have done a lot of trials. So it's just a nice thing for the techniques, especially fMRI and MEG.
Nice, Isabel. Thank you. Thank you very much.
So thanks, Isabel. I think we have no questions at this moment. So now I will invite the next speaker, that's Tayani Hamus. Tayani has just finished her PhD in computer science at the University of São Paulo. During her PhD, she stayed part of the time at UCL in the lab of Janaína Mourão Miranda, where she met Isabel during her PhD, her postdoc. And now Tayani is here, and she will work with us as a postdoc in our lab at LabNEC. And today she will talk about the work that she conducted during her PhD. So Tayani will talk about brain behavior associations of children with typical development and autism spectrum disorders. So welcome, Tayani.
Hello, sorry, I'm just trying to share my screen. Okay. Can you see the slides? Are you still seeing?
Yes.
The first slide, right? Interesting, I don't see it, but that's fine. If you can see, it's fine. Okay, so hello everybody. Thanks for joining us today. Thanks for inviting me for this talk. My name is Tayani Hamus. Today I will present a work I did during my PhD in collaboration with University of São Paulo and University College London. This work is called Brain Behavior Associations in Children with Typical Development and Autism Spectrum Disorder. It is estimated that autism spectrum disorder, ASD for short, is a characteristic present in 1% of the world population. The main characteristics include deficit in social interaction and communication, restricted interests, and repetitive behaviors. The severity of the disorder presents a broad spectrum ranging from high-functioning autism, in which the person is able to study, work, and lead an independent life, to cases in which the person has severe cognitive delay and might not develop any verbal communication. Because of this wide variation in characteristics, it arose the idea of doing a multivariate analysis to create a stratification of subjects based on the variation in the brain and behavior data. So we used an Fmri data from the Abide2 database. We used 394 subjects, of which 217 are with typical development, and 177 is with autism spectrum disorder. We performed the preprocessing of the data following the Athena pipeline. This pipeline includes the time slicing correction, movement correction, and scrubbing procedure, among other steps. We used an atlas of functional parcellation to discriminate brain regions, and we obtained 316 regions of interest. We computed the correlation between every pair of regions, and we take the bottom half of the correlation matrix to avoid duplicates. The correlation values represent the strength of the functional connectivity between two regions, and the brain connections are the variables we used in the analysis as the brain data. For the behavioral data, we selected 3 psychometric scale instruments: the social responsiveness scale, that is related to social behaviors; the child behavior checklist, that's related to expression of behaviors and emotions; and the behavior rating inventory of executive function, which measures capabilities related to the executive function. We also used variables of IQ, age, sex, and hand use preference. In total, we have 30 variables in the behavioral data. We only used subjects with answers for at least 2 of the 3 scales, and the missing data were completed with the median of the variable across the sample. To identify the association between brain and behavior data, we used the sparse partial least squares method, also known as SPLS for short. Each subject is represented by their brain connectivity data and their answers to the psychometric scales. The X and Y matrices contain the brain and behavior data for all subjects. We enter these matrices in the SPLS, and it will assign weights to the variables, which are the vectors U and V. This is done in a way that the data projections of X and Y on the weights U and V have the highest covariance. We call these data projections in the weights, the brain score, and the behavior score. These score vectors contain 1 value per subject. By representing each subject by their respective brain and behavior scores, we can create a dimension of variation in the characteristics of the population. The idea is that when placing subjects in the chart, we can see a variation of characteristics from typical to atypical. So this is the plot that I call the subject stratification. Since SPLS is a sparse method, it uses 2 regularization parameters, here called CU and CV. We need to optimize these parameters. And for that, we will use a sorry, I forgot. I forgot how we call it. It's a multiple holdouts framework proposed by the UCL team. The first step is to draw 8% of the subjects to form the optimization set, and the remaining subjects are going to form the holdout set. Using only the optimization set, we again draw 8% of the subjects to create a training set and 20% to form the validation set. We do this 50 times, obtaining 50 different splits of the data in training and test set. For its combination of CU and CV parameters, we adjust the SPLS model in each of the 50 training sets and apply them to the 50 test sets. We use the average of the result of the 50 splits to select the best pair CU and CV. We adjust the SPLS model with the selected parameters throughout the optimization set and then apply it to the holdout set. To assess the statistical significance of the results, we use a permutation test. The top part of the image represents the SPLS training in the optimization set with the selected regularization parameters. We project the data of the holdout set on the obtained weight vectors. We obtain the score vectors and compute the correlation between them, represented here by whole model. At the bottom of the image, we have the permutation test. We exchange only behavioral data to break the association between brain and behavior data. We do the same process by training SPLS with the selected regularization parameter. And again, we project the holdout set on the obtained weight vectors. We obtain the score vectors and calculate the correlation between them, here represented by a whole pair. We repeat the permutation process 1,000 times. The p-value is calculated by, as the number of times that the correlation between by the permutation is equal or greater than the original correlation obtained, the one I called whole model in the original set. There could be difference in the results due to the split of the data into optimization and holdout sets. So we repeat 10 times the whole process of parameter optimization, SPLS training, and obtaining the significance by permutation test. And we get results for 10 different splits of the data. We report the results with the lower p-value and greater correlation. We then report the brain behavior association that obtained an out-of-sample correlation of 0.383 and p-value lower than 0.01. Bonferroni corrected for 10 splits of the data. The scores obtained in the brain behavior association were used to create the dimension of variation of the subjects. Each point here represents a subject. The red dots are subjects with typical development, and blue dots are subjects with ASD. We can see that the typical development subjects are more concentrated at the bottom of this plot, and subjects with ASD are more spread out. Among the behavior variables, those with higher values in the plot are the most important for these associations. Thus, we see that the variables in the SRS scale are the most important. They are association with social behavior, which is clearly related to autism symptoms. We create this plot using the correlation between the scores and the original variables. To create this increase and decrease plots in the brain, we again use the correlation between the scores and original variables and multiply by the sign of the average connectivity of the population. In blue, we have the connections that show the decrease, and in red, the connections that show increase in the subjects presenting the highest scores. From our plot of subject stratification, we saw that the subjects with highest scores are those diagnosed with ASD. So we expect to see this decrease and increase in connectivity in subjects presenting more autistic characteristics. In the summary plot by nodes, we can see better the networks involved. The functional networks with decreased connectivity are mainly the default mode network in green, the somatomotor in dark blue, and the frontal parietal in red. The networks with increased connections are mainly visual in light blue and somatomotor in dark blue. To better visualize the connectivity between networks, we created this plot. We can see that we have more decreased connections within the default mode network and within the somatomotor network. And we have increased connections mainly between the somatomotor and visual network and between somatomotor and default mode. So in conclusion, we found an association between fMRI data and behavioral characteristics that seems to capture information about the diagnosis of autism. We could see in the subject stratification plot that there was a difference in the disposition of subjects with and without diagnosis of ASD. Subjects with typical development were more concentrated, while subjects with ASD were more spread. This arrangement is compatible with the spectral nature of the disorder. The results were consistent across the 10 divisions of the data, and we believe they are likely to generalize well to new data. Thank you.
Thank you, Tayani. It's a very interesting topic. Let me see if we have questions here or.
Yes, I have.
Oh, Plastin, okay.
Okay. Thank you, Tayani, for your presentation. Very nice work, very interesting. Have you already presented your thesis?
Yes, it was last Friday.
Oh, congratulations.
Thank you.
Yeah. And my question is about the method used to validate the classification process. Why didn't you use, for example, tenfold cross-validation? Any reason for avoiding it? You used multiple holdout. Any reason for that?
Yeah, well, this is based on the work made on UCL by the UCL team, and they have a couple of works showing that this is a better solution for not getting false positives. So because the framework implements this way, I used it this way, but it wasn't my choice. I'm just following their work.
Yes.
And well, they believe this is a better choice.
Yeah, it seems to be an interesting choice, but I would like to know the reason, if there is some statistical reason for one method be better than the other. But okay.
Plastin,
nice.
may I can answer, I think. I don't know. It's very expensive, computational expensive to do the permutation in all the steps. So in this way, we can do the permutations. Can do the permutation only in the final. Makes sense, Tayani? I think it's one of the reasons. It's because it's less
expensive.
Less expensive in terms of computational.
Okay.
I'm not sure if this is the main reason. I know that they always say that this multiple rollout framework is better for controlling false positive and false negative. So this would be my answer.
Nice. Okay. Thank you very much, Tayani.
Thank you.
Okay. Any other questions?
I have a question for Tayani. Just to my question is regarding the use of this approach for another clinical conditions, another psychiatric disorders. What do you think is possible? This latent space is interesting for the other.
Yeah, for sure. I believe this is easily adaptable for any other type of disorder. We could have the Fmri data and the questionnaires, the scales, and it could be applied for many other types of disorders. It was already applied to a depression database, and I believe that we don't need to change anything on the framework for that.
And it's possible to identify vulnerabilities using this space, you know, looking for the brain scores and the behavioral scores, plotting the data, you can see a separation, but you can see the vulnerability maybe for a new patient or new person. So
yeah. People that still don't have the diagnosis, if they are more in the group of the people who have the diagnosis, maybe they are more vulnerable of developing the diagnosis. Yeah, for sure.
Okay, thank you, Tayani.
Thank you.
Do we have any other questions from the beginning, Plastino? Any questions that's in the chat that we didn't ask?
No. I think all questions were answered.
So I think we have finished for.
Yes, sir.
I think
we have a question chat
from Orlando.
Yes.
Oh, so let me.
To Isabel.
Okay. Isabel. Orlando is asking about have you tried to classify famous versus non-famous face?
Yeah, I think I already answered a little bit about it, but we started with this, but the thing is famous and unfamiliar faces are processing differently in terms of time. For instance, the famous faces are processing parallel, and the unfamiliar faces are has more serial processing. And if we compare the two conditions in EEG, for instance, it's difficult to find differences because although they exist, because of these differences in time processing. So we thought that it would be more informative to compare to have the conditions for the faces unfamiliar and familiar in different models. So we could observe how the features, how the spatial and also the temporal characteristics of the stimuli would appears in a more range of possibilities when you are using a not direct model uniting the two. I don't know if I was clear about the answer the question.
Well, I think so. So before calling Deborah and Leticia to finish, so I'd like to, I think we have no other questions. So I'd like to thank a lot for the opportunity of being here and to thank Leticia and Deborah for coordinating this project and this workshop today. And so Deborah and Leticia, do you want to talk to the final words for today?
Okay, Miss, thank you. Plastina, do you want to say something? No?
No, nothing special. Only that I'm very happy to be here. It was a success, this workshop. Thank you very much for all the presentations, people. It was great. Thank you very much.
Okay, so I will finish the workshop. Deborah cannot stay until the end. Unfortunately, she received a bad news. And so in my name and her name, I would like to thank all the speakers for being here. As I said, the schedule is very busy, and so it's an honor to be here with you. And I would like also to thank the audience and the questions. I'm sure today was a very productive day. So thank you so much for everyone. Bye-bye.